Hi everyone and welcome to the internet. What we're going to be doing in today's lesson is having a look at reversible reactions. So what we're actually moving on to is the third and final part of C5, which is all about equilibria. To start us off though, what we've actually got here is an example of a 6-mark question. It's actually from the last specification, so not the current one, the one before that, but it looks at rates of reaction. So what I'd like you to do is have a go at answering this. It is a 6-mark question, so that does mean that we make sure we use capital letters and a full stop at the end and write in a sentence, not just random words. And make sure you answer both of the points. So one of the key ways that people throw away marks on the 6-mark question is they only answer half of it. So what we can see here is there are two parts to the question. The first one, which experiments support the conclusion, and the second part is to explain using the reacting particle model why. So I'm going to give you the usual 6 minutes to actually answer this question properly because it's 6 marks, so 6 minutes is a good time frame to use for it. So plenty of time, read the question carefully and then write your answers in your book, making sure you answer both parts of that question. So let's have a look at how this is marked then. As with all of these 6-mark questions, then it's actually split up into bands. So hopefully no one got obviously the level 0, which is basically no marks at all, and literally that statement just says nothing worthy of credit. We're going to assume no one got that, I hope. So to get the level 1, which is 2 marks, assuming you managed to write a coherent sentence, then what we needed to say is that the rate of reaction increases when the temperature increases. So if you've got a sentence in your answer that just states that as the temperature increases, the rate of reaction increases, you can get your first 2 marks. That's it, one sentence, all we needed. To then move up to the level 2, we need to give the explanation using the reacting particle model. So what we then go on to say is, in addition to the rate of reaction increases when the temperature increases, we say that at higher temperatures the acid particles have more energy and move faster. If you just said particles, that's fine. And we then talk about there being more frequent successful collisions. If you only had one of those points, then you only get one of those marks at the level 2. So if you'd said the rate of reaction increases when the temperature increases, this is because at higher temperatures the particles have more energy and move faster, you've got 3 marks. So what we need to do is talk about the fact that particles have more energy, they're moving faster, and then they've got more frequent successful collisions. That go-to phrase we're going to use in rate of reaction questions. If you've got those first 3 sentences, you've got 4 marks. And then the last bit, the second part of the question, the bit that we frequently forget to do, is to identify the experiments that support this conclusion. And in this case, the 2 experiments that supported it were experiments 1 and 3, because there the temperature changed, but nothing else did. Because remember, if we're trying to get experiments to prove something, we've got to only change one of the variables, the one we're investigating. If you put experiments 1 and 3 support the conclusion along with the other bits about our collisions, then you can get your level 3 6-mark answer. So you can see here that when we are looking at these 6-mark questions, despite the fact they may give you the best part of half a side of A4, then we did it in 4 sentences. And that is, I promise you, 6 out of 6 on there. So it's not always vast quantities of writing needed. Some of them will need more, don't get me wrong, but some you can be very clear, very concise and get top marks on it. And the key thing as an examiner and one of these markers, the thing I hate most and the thing lots of markers hate is the excessive waffle you lot do. So when you are going on to the additional pages, unless you happen to have large handwriting, chances are you're waffling. And please don't. You're wasting time in the exam writing extra things that just aren't needed. So clear, concise answers. Give yourself a mark out of 6 based on what you've got. So what we're going to be looking at in today's lesson then are reversible reactions. Now, when we talk about a reversible reaction, this is one where, of course, we've got our reactants that make our products, but those products can then react together to form our original reactants. So this is a reaction that goes both ways. And what we actually have is a very distinctive symbol that we need to know. So you can see it's got half arrow going to the right and half an arrow going to the left. Wherever you see that symbol, we have a reversible reaction. So write down those 2 points, make sure you highlight that symbol, make it stand out, because that has been a 1-mark question before, just asking you what symbol tells you it's a reversible reaction. let's actually have a look at an example of this so we know what we're talking about. So the example I'm going to give you is a substance that you should be quite familiar with at school, which is copper sulfate. Now we're going to be looking at the hydrated copper 2 sulfate first of all, and if you look, that's the blue stuff on the left, so that's hydrated copper 2 sulfate. And this will undergo a reversible reaction to form anhydrous copper 2 sulfate, which is the white powder on the right, and water. So what we actually do here is we take copper 2 sulfate, which has been joined with the water there, and we're then going to basically separate the water to make the anhydrous copper 2 sulfate, so just copper 2 sulfate with no water, and the 5 water molecules separate. But what we can also do is we can take those products of the anhydrous copper 2 sulfate and the water molecules, and then they can recombine to form the hydrated copper 2 sulfate. So this reaction goes both forwards and backwards. So make sure you've got both the word and the balance symbol equation written down as a good example here. I'll leave this up for about another minute to give you a chance to get the numbers in the right places. And of course, remember your subscript numbers. You'll notice between the copper sulfate and the water in the hydrated copper sulfate, there's a little dot. So that's how we denote that something is hydrated. We put our chemical formula, a dot, and then the water molecules after it. What I'd like you to do then is have a go at writing down those two reactions, the forward reaction and the backward reaction. One point to note is that when we're writing just the forward and just the backward reaction individually, then we don't use the reversible reaction sign, we just use a standard arrow. So have a go at writing down the forward reaction and writing down the backward reaction for me. So hopefully our forward reaction reads as CuSO4.5H2O, normal arrow, CuSO4 plus 5H2O, and the backward reaction is CuSO4 plus 5H2O, the arrow, and then CuSO4.5H2O. So all we're doing, the forward reaction starts on the left and works to the right. The backwards reaction starts on the right and works to the left. So give yourself a tick for each one of those you got right. So let's now have a little look at this experiment actually being carried out in a video.
So the equipment we need to carry out this reversible reaction, some water, a boiling tube, some blue copper sulfate, clamp stand, Bunsen burner, and spatula. Okay, so the first thing you need to do is you need to get your boiling tube and attach it to the clamp. What you have to make sure you do is you clamp it near the neck of the tube. You don't want it too far down because you're going to be heating it this side. And also you can see you want it at a slight angle. So if anything does come out of there, you know which direction it's going to move in. Once you've attached your boiling tube, you'll then take your copper sulfate and then you'll use your spatula and you will fill in carefully. 2 spatula fulls of copper sulfate. Be careful not to drop it. Okay. Once you've done that, just make sure that the clamp is tight before the next step of heating it. So you want to make sure it's on a safety flame first. So this valve at the bottom is closed. Then you turn it so you get a nice roaring flame, and then you place it under your test tube to start to heat the copper sulfate. So now the copper sulfate has gone white, you need to move the Bunsen away and turn it off. So now you need to leave it and let it cool for about 3 minutes. While you're doing that, you can draw the apparatus and show what you've done. Okay, so now we want to reverse the change, and so we're going to add some water. So fill the pipette up, and then you want to add the water, the copper sulfate. And you can see the colour, the blue colour, has returned. And you don't want to add too much, otherwise it'll become a solution and ruin the experiment.
What I'd like you to do then is, on the screen now, we've got 4 sentences with some missing words, and the words you need are all listed at the bottom. So see if you can have a go at finishing off those 4 sentences using the missing words for me. I'm going to give you about another 3.5 minutes to do that. Let's make sure we've got the right words in the right places. As always, tick any you've got right, any you've got wrong, make sure you put the correct answer in. So to achieve the forward reaction, we had to heat the powder, as we saw with the Bunsen burner in our video. This provided the energy needed to decompose the hydrated copper 2 sulfate. The forward reaction was endothermic because we were supplying that energy to it. Remember, if we're heating something, we're actually supplying energy that's being taken in order to separate those atoms there. When we added water to the anhydrous copper 2 sulfate, an exothermic reaction occurred. If we know the forward reaction is endothermic and we know that the backward reaction is just the opposite, then if it's endothermic in the forward, it must be exothermic in the backward. And vice versa. If the forward reaction had been exothermic, then the backward reaction must be endothermic. So give yourself a score out of 5 for me on that one, and obviously make sure any errors you have corrected them yourself. The last part of today's lesson, we need to consider a situation called a dynamic equilibrium. But before we can do that, we need to understand what we mean by an open and a closed system. When we talk about a closed system, then this is one where no substances can either enter or leave. And a really good example of this is a flask with a stopper in the top. There obviously nothing can enter because the stopper's there, and nothing can leave because of that same stopper. So anything that stops things entering or leaving, that is a closed system. An open system is, as the name suggests, one where substances can enter or leave it. So that would be a beaker without a lid on it, where we're producing a gas, for example. So make sure you've got our closed system definition written down for me. What we're going to do then is we're going to consider a closed system, so one where no substance can enter or leave, and a reversible reaction occurring within that closed system. And what we actually find is that when this reversible reaction is occurring within that closed system, then the rates of the forward and the backward reactions will become equal. And at the point that that happens, we have an equilibrium. Now, because we still have the forward and backwards reaction still happening, then it's not static. We refer to it as a dynamic equilibrium. So equilibrium because the forward and backward reactions are equal to one another, and dynamic because both forward and backward reactions are happening all the time. So make sure we've got those 3 sentences written down and we know why it's called a dynamic equilibrium. So dynamic because the 2 reactions are happening all the time, equilibrium because they're happening at the same rate and therefore they become equal. And what we actually find then is that when we've got our reaction mixture at equilibrium, then the concentrations of all of the reacting substances will remain constant. Because if the forward reaction and the backward reaction are happening at that same rate, then it means that as soon as we're forming that new product, it's also being used as a reactant. So the concentrations of the reacting substances will remain constant. Make sure you've got that last sentence written down for me. Final thing for today then is the plenary. So 3 questions for you all to have a go at. Obviously make sure that you do read the question carefully and then write your answers fully in your books. So I'm going to leave this up for about 4 minutes today, but as always, if you need longer to do it, then just hit pause and take as long as you need to think about the questions properly.